Hello. Today we will be looking at how we can calculate the wavelength of a photon with enough energy to remove a valence electron, also known as ionization energy. As an example, we will be using question 5b from the 2019 AP Chemistry exam. The complete photoelectron spectrum of an element at its ground state is represented below. And now for this part, we need to calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom of the element represented by this photoelectron spectrum to the left. So let's take a look at the information that's given to us in this graph. We are given the binding energies of various orbitals of this ground state element. And remember, we only care about the energy to remove a valence electron from this element. Valence electrons are the easiest to remove because they experience less attraction to the nucleus. So we need to find the orbital that requires the least amount of energy to take an electron from, which would be this one right here because it is bound by weaker forces. The question asks us to find the wavelength, which we'll represent with a lambda. There are two equations we have at our disposal that could be used to help us find the wavelength. E energy equals Planck's constant times frequency, and the speed of light equals the wavelength times frequency. The second equation has the wavelength that we need to solve for, and the first equation has the energy we need to ionize, as we found earlier. Both equations have frequency in common, so we can start by writing each equation in terms of V. V, frequency, equals E energy over Planck's constant. And V, frequency, equals the speed of light divided by lambda, wavelength. Since both equations are now equal to the same thing, we can write them equal to each other. E over H equals C over lambda. And since we are trying to find wavelength, we can set the equation in terms of lambda equals Planck's constant times the speed of light over energy. And since both Planck's constant and the speed of light are constants, we can now find wavelength, which is Planck's constant 6.626 times 10 to the negative 34 joules seconds times the speed of light 2.998 times 10 to the 8 meters per second. And all of that is over our energy, 0.980 times 10 to the negative 18 joules. And if we plug this all into our calculator, we should get 2.03 times 10 to the negative 7 meters. And this length that we found is the wavelength that we were trying to find in the first place, the wavelength required for first ionization.